Hi there. So what I'm going to do today is I'm going to talk about rational functions. This is this is two sections, 11.4 and 11.5. So just like with our polynomial functions, I combine two sections. I'm doing the same thing with our rational functions. Okay, so we have sections 11.4 and 11.5. And we will talk about rational functions. These are a ball. Okay, so you might ask, what is a rational function? Well, I'll call him R of x, just based on total lack of originality, R for rational. What it is a ratio of two polynomials. So P and Q are both polynomials. Okay, so the one thing that we have to watch out about when we deal with rational functions is we've got domain issues. Because we have a denominator, we've got to pay attention to where our denominator might be equal to 0. So what I would like to do to start motivating rational functions and just various ideas that go on with our rational functions is take what's perhaps considered the simplest rational function and graph it, and then talk about the characteristics of the graph. Okay? Now, you might wonder, well, how are we supposed to graph it if we don't know about rational functions? Well, the beautiful thing is you can always go back to your x, y, t table. So, let us take this rational function, 1 over x. Okay, this is a degree 0 monomial. Okay, there's only one term, and this is a first degree monomial. All right, so what I want to do is make a t-table so we can plot some points and kind of get an idea as to what's going on. Now, one thing we note is x can't be 0. Okay, can't divide by 0. So we won't even start there. If I plug in x equals 1, then I have 1 over 1, which is 1. If I plug in x equals 2, I have 1/2. If I plug in x equals 3, I have 1/3. So notice, I could go all the way to plug in 100, and my function value would be 1/100th. So do you see how, as our x values are getting large, our function values are getting closer and closer to 0? Okay, that's one comment that I would like to make. Now, while I'm on the topic of getting closer and closer to 0, let me say this. 1 over x can never be equal to 0. Okay, so while this might approach 0, it can never actually be equal to 0, right? Precisely because when you have a fraction equal to 0, that means your numerator has to be 0, but our numerator here is constantly 1. All right, well, let me ask you this. Okay, it was curious. We couldn't plug in 0, but let's find out what happens as we get a little closer to 0. For example, suppose I want to plug in x equals 1/2. Well, if I have this function and I plug in 1/2, I have 1 over 1/2. Well, remember when you divide by a fraction, you multiply by the reciprocal, so I claim that 2 comes out. Wow! Now, what happens, for example, if I plug in 1/3? Well, if I plug in 1/3, I have 1 over 1/3, which is 3. Just like I picked 100 here, what would happen if I plugged in 1 over 100? Again, when you divide by a fraction, you multiply by the reciprocal, you get 100 out. So notice, as we're getting closer to this forbidden point, our function values are getting absolutely huge. All right, so let's plot this, at least get the general idea. 1, 1. When we're at 2, we're at 1/2. So we see that it's going to get closer and closer to 0. And notice, when I plugged in 1/2, I was up at 2. When I plugged in 1/100th, I was all the way up at 100. Okay? So, we're not done. We're only halfway through it because we can certainly plug negative numbers in. Again, the only limitation we have here is that we can't plug in 0. So, let us make a t-table for our negative portion. Okay? If I plug in -1, well, 1 over -1 is -1. If I plug in -2, then I claim I get -1/2. Okay? Very similar thing going on here. So again, if I plug in -3, I'll have -1/3. So what I'm going to do now is say, well, what happens if I plug in -1/2? In other words, get closer to 0, the forbidden point, from our negative direction. Well, 1 over -1/2 is -2. I claim if you plug in -1/3, you're going to get -3. If we go to the extreme and put in like -1/100th, well, again, we're going to get -100. All right, so if I plot these points, what I'll see is my graph looks like this. All right, I really like starting out with this function here. What I want to do is I want to talk about certain properties and characteristics. Okay? Notice a few things. Notice that as x goes to infinity, in other words, as my x values get really large, and as x goes to -infinity, as x gets really small, my function values are approaching 0. Okay? When this sort of thing happens, in other words, when you say as x gets really large or really small, your function values approach some number, that's called a horizontal asymptote. And we've talked about those, for example, when we were talking about our exponential function. Okay? Now, I claim we also have another thing going on here. Notice, as my x values are approaching 0, do you see how either my function values are shooting up to positive infinity or shooting down to -infinity? When that sort of thing happens, we have what's called a vertical asymptote. Okay? These ideas are super important. Okay? In order to graph our rational functions, one of the first things that we're going to do after we find any x and y intercepts is we're going to find our asymptotes. So let me say this. Okay? What I would like to do is tell you that you have a horizontal asymptote if, say at the point, I'll call it L, if as x goes to positive or -infinity, your function values approach that. So, for example, here we have a horizontal asymptote at 0. Okay? So let me say at y equals L. Now, in a similar manner, we can talk about our vertical asymptote. We could say we have a vertical asymptote at x equals, doesn't really matter what we call it, we'll call it P, if as x approaches P, our function values either fly off to positive infinity or shoot down to -infinity. Now, something that I would like to mention to you is this. Notice we have a vertical asymptote here at x equals 0, right? Because as we approach 0 from the right-hand side, our function value shot up to positive infinity. As we approach 0 from the left-hand side, our function values approach negative infinity, okay? Remember, this function that we looked at is 1 over x. What was the one forbidden point we couldn't plug in? We could not let x be equal to 0, but notice that was precisely what our vertical asymptote ended up being, okay? That's not a coincidence, and we'll get there in a moment, okay? What I would like to do first is talk about how to find your horizontal asymptote, and then we'll talk about how to find your vertical asymptotes. Okay, so notice when we're talking about our horizontal asymptotes, we don't care what happens in this portion of our graph. When we're interested in the horizontal asymptote, we're asking what is the long-term behavior? What happens as x gets really large, or what happens as x gets really small? Okay? So I claim, really, okay, let's say that we have two polynomials. Don't let these letters mess you up, please. So suppose that's the shipwreck in my numerator, and this is my denominator, okay? What we want to know is what happens as x gets really large or really small, okay? Well, I claim as x gets super large or super small, none of these terms matter as much. What's relevant are your first terms, okay? What's relevant is what happens here, okay? Again, because as x gets large, when you raise it to a power, well, this is a higher power than so on and so forth. This is the only term that's relevant, okay? So, well, what happens as x gets really large or really small? I claim that depends upon the degree of your numerator and the degree of your denominator, okay? For example, with 1 over x, as x gets very large, well, we have 1 over a really large number. Isn't that going to go to 0? It absolutely is. And notice the degree of my numerator was actually less than the degree of my denominator. So, here are your steps. To find your horizontal asymptote, what you want to do, again, is consider the degrees. If the degree of your numerator is less than the degree of your denominator, okay, so I mean, I could have, say, x cubed over x to the 10th, even. And yes, we could simplify this, but let's just consider our first terms. Okay? Here, the degree of our numerator is certainly less than the degree of our denominator. Well, listen, as x gets really large, your denominator is going to overpower your numerator, which is going to take this whole thing to 0. So whenever the degree of your numerator is less than the degree of your denominator, your horizontal asymptote is always y equals 0. If the degree of your numerator is greater than the degree of your denominator, there is no horizontal asymptote. Why? Well, because if I have like x to the 10th over x cubed, as x gets really large, this whole thing is just going to fly off to infinity anyway. or to negative infinity, depending upon the degree and the power, etc. Okay? So, what is important to keep in mind is paying attention to what the degrees are. And lastly, the only other situation we haven't thought about is what happens if the degree of the numerator is equal to the degree of the denominator. Okay? Then both terms matter. You do have a horizontal asymptote. It's essentially the ratio of your leading coefficients. So you take the number in front of each of those x raised to whatever power it is and form a fraction, and that is precisely what your horizontal asymptote is. So I believe we had something like a to the, pretend we have this. The degree of our numerator is equal to the degree of our denominator. So essentially these guys kind of cancel each other out, and it's just the ratio. It would be a to the n over b to the n. Okay? Let me show you some examples here. Let's practice finding some horizontal asymptotes. Okay, so what if I have y equals, say, 3x over 2x squared plus 5? The degree of our numerator is 1, the degree of our denominator is 2. Notice, as x gets really large, this guy's going to overpower him. The degree of my numerator is less than the degree of my denominator, and I think you'll grant me that if my denominator overpowers my numerator, this thing's going to fly to 0. And in fact, our horizontal asymptote is y equals 0. What if I have, say, 5x to the 4th over 3x cubed minus 1? What would be our horizontal asymptote here? I claim there is none. The degree of my numerator is greater than the degree of my denominator. Think of it this way, as x gets really large, your numerator is going to get really large. So it's not like your function values are going to be approaching anything. All right, what if I have y equals, say, 2x plus 3 over 5x minus 17? Notice here, the degree of my numerator is equal to the degree of my denominator. So, my horizontal asymptote is the ratio of the numbers in front. It's the ratio of the leading coefficients, so it's 2/5. All right, so there we have at least this much. Let's do one more. What if I have y equals negative x squared plus 15 over, say, 3x squared minus 17. Okay? Notice the degree of my numerator is equal to the degree of my denominator. So I'm going to have my horizontal asymptote be the ratio of the leading coefficients. I have a negative 1 over 3. Okay? So that is what we have with our horizontal asymptotes. Don't worry, we'll get a lot of practice finding these because we're going to be graphing a whole bunch of them. All right. Vertical asymptotes. The way you find them, you set your denominator equal to 0 and solve. That's it. Okay? So, essentially, you have a vertical asymptote, again, at x equals a, if as x approaches that value, your function values either shoot up to positive infinity or shoot down to negative infinity. Okay? So, now that we've laid down our horizontal asymptote and our vertical asymptotes, and we've already discussed our intercepts, we're ready to graph. Before we graph, there's one thing that I would like to do just as a side note. Okay? We've talked about inverse functions. And what I want us to practice doing is this. Let us practice finding the inverse of a rational function. So, suppose I have this rational function. And I want to find my inverse. Okay? First off, trust me, he's 1 to 1. We're okay here. Okay? So, let us find the inverse for this function. You may or may not remember how to find the inverse, but that's why it's great that we're going through this again. First off, we can write this as y is 4 minus 3x over 5x minus 4. The first thing that I like to do when I'm finding my inverse is I switch my x and my y. Remember, your first step is to switch x and y. Your second step is to solve for y. All right, well, the reason why I'm doing this example is because you might not remember how to find the inverse of something as complicated looking as this. Well, what's the first nasty thing we look at here? We've got a denominator. So, our first step in order to find the inverse of this function is to get rid of our denominator. How do we get rid of denominators? Don't we multiply both sides by him? So I claim if I do that, I have x times the quantity 5y minus 4 is equal to 4 minus 3y. All right, remember our goal is to get y alone on one side. So our next step is then going to be distribute. We have 5xy minus 4x is 4 minus 3y. Okay? Now, if we want to get y equals, why don't we move all of our terms with y to one side and everything else to the other side? In other words, I'll move him over here and I'll move this 4x over there. If I do that, well, how do I move a negative 3y? I add it to both sides. How do I move a negative 4x? I add it to both sides. Okay, again, our goal is to have y equals. Can't I factor out a y? And I'm left with 5x plus 3. We're almost there. We have y times this mess. How do you get rid of this mess? Divide. So, I claim we will then have y to be 4 plus 4x over 5x plus 3. And that is our inverse. Okay? I just wanted to go through that with you to be sure that you're able to do such. Let me say this to summarize. To find the inverse of a rational function, I'm just going to summarize our steps. First thing that you do is you switch x and y. The next thing that we did is we multiplied both sides by the denominator. Then what we did is we distributed. And then we use our algebra to solve for y. In other words, we get all of our y terms on one side, everything else on the other side. Okay? Notice there was a little factoring involved. You may need to factor. Okay? All right. Well, I'm glad we went through that. So, what I would like to do now is outline the steps that we're going to use in order to graph our rational functions. And then we're going to play. So, in general, to graph the rational functions, step 1, find your intercepts. Both your x and your y intercepts, if they exist. Number 2, you want to find both your horizontal and vertical asymptotes. And then step 3, test points as needed. Now, the way this is written out, it sure looks pretty mellow, doesn't it? Okay, so let's go through and graph a bunch of different rational functions and see how our graphs look. Let us take, for example, well, let's just take this guy. He's a really relaxed example. Okay? So, this is our goal, to graph him. First off, we want to find intercepts. To find our x-intercept, don't we set y equal to 0? In other words, we set our rational function to be equal to 0. Well, remember, a fraction's only equal to 0 if your numerator is equal to 0. Our numerator is constant here. There are no x-intercepts. That means the graph never touches or crosses the x-axis. That's of crucial importance. Our y-intercept. Well, to find that, you set x equal to 0. If I set x equal to 0, I claim I get y to be 1. So it goes through the point 0, 1. All right, we got that done. Next, let's find our asymptotes. Our horizontal asymptote. Well, remember, to find your horizontal asymptote, you have to consider the degrees. In this case, the degree of my numerator is less than the degree of my denominator. Therefore, y equals 0 is my horizontal asymptote. The way I indicate horizontal asymptotes is with a dashed line. That's also how I identify vertical asymptotes. Now, one quick comment I want to make. You can touch or cross a horizontal asymptote. Horizontal asymptotes, remember, only tell you the long-term behavior. They only talk about what happens as x gets super big or super small. Okay? So, you can touch or cross a horizontal asymptote. However, you cannot touch or cross a vertical asymptote. Okay? Let's find our vertical asymptote here, and I'll show you exactly why. Okay, well, how do you find your vertical asymptote? To find your vertical asymptote, remember, you set your denominator equal to 0, and you solve. So, x equals -1 is your vertical asymptote. Okay? All right, well, let's now think about what we have. First off, notice I have a horizontal asymptote at y equals 0. What does that mean? That means is as x gets really large, my function values are going to approach 0. Now, funny things can happen over here because you can touch or cross your horizontal asymptote. However, didn't we see that there's no x-intercepts? In other words, this graph never touches or crosses our x-axis. Therefore, I know that my graph is going to look like this. Again, it can't jump down because then I have an x-intercept. It's not going to fly up because then I don't have my horizontal asymptote. Okay, so a lot of the graphing of rational functions comes just from knowing what it means to be a vertical asymptote or a horizontal asymptote. All right, now let's see what happens as we approach our vertical asymptote. Remember, as you approach a vertical asymptote, by definition, your graph either shoots up to positive infinity or shoots down to negative infinity. I claim we have no choice here but to shoot up. Why? Because notice, if I went down to negative infinity, wouldn't I be crossing my x-axis? And if I cross my x-axis, that means I have an x-intercept. But I don't have any x-intercepts. So I know that this is going to shoot up. And there's half of our graph already. Okay, we will need to take a test point to see what happens on the other side of our vertical asymptote. So we can certainly do that. So now I'm at step 3, take a test point. Well, why don't we test -2? I claim we really only care about the sign, whether it's positive or negative. You'll see why. Notice if I plug in -2, -1 comes out. So here's -2 and here's -1. I claim I have my graph. Why? Because I have a horizontal asymptote at 0. So I know I've got to approach my horizontal asymptote, and I know I don't cross my x-axis because we don't have any x-intercepts. And as I approach my vertical asymptote, remember, by definition, I either shoot up to positive infinity or shoot down to negative infinity. I claim I can't shoot up because that means I would have to cross my x-axis, and for like the 7th time, we don't have any x-intercepts. Therefore, we shoot down to negative infinity. Now, could we have done this graph using our translations? I claim we could have. Why? Because we've already graphed, if f of x is 1 over x, we've already graphed that. Aren't I graphing f of x plus 1? In other words, I'm adding 1 inside. What does that do for our shifts? Well, remember, when you add inside, it moves it to the left that many units. And notice that's exactly what we did with that graph. Isn't that cool? Well, I think it's really exciting. All right, let's do some more. What if I have y equals x minus 3 over x squared plus x minus 2? Okay, start out with a clean graph here. First step, intercepts. Okay, to find our x-intercept, remember you set y equal to 0. Well, again, you guys, if you set a fraction equal to 0, it's only equal to 0 if your numerator is equal to 0. So I claim x equals 3 is our only x-intercept. All right, how about our y-intercept? Well, to find your y-intercept, you set x equal to 0. If I plug in x equals 0, I claim I'm left with a -3 in my numerator. These terms will go away, a -2 in my denominator, so 3/2. There we go. Okay? Next, horizontal asymptote. Well, again, consider the degrees. Notice here the degree of my numerator is less than the degree of my denominator. So again, y equals 0 is my horizontal asymptote. Notice we have a horizontal asymptote at y equals 0, and we also have an x-intercept. Again, that's okay, because your horizontal asymptotes talk about your long-term behavior, not your short-term behavior. Okay, vertical asymptote. Well, how do you find that? You set your denominator equal to 0 and solve. Well, what's the best way to solve a quadratic? Factor. Y'all agree it's x plus 2 times x minus 1? I have the product of two things equal to 0. So either my first guy is 0 or my second guy is 0. So I claim here I actually have two vertical asymptotes. I have a vertical asymptote at -2, and I have a vertical asymptote at 1. All right, a lot of question marks in this graph, okay? This is probably going to be one of the more complicated ones we do. Notice your vertical asymptotes separate your graph into different regions. You have to consider each region separate precisely because you can't touch or cross it, okay? So what we now need to do is take some test points to see what is going on with this graph, okay? I'm going to start over here. First off, I need to know what happens as I approach this vertical asymptote, okay? See, right here, I'm right now on my axis. I could either shoot down or shoot up, and either one would be consistent. So what I'm going to do is I'm going to test x equals 2. Now, all I care about is the sign. In other words, is it above my x-axis or below? So if I plug in the value of 2, again, I'm not going to compute any numbers. I'm just going to talk about positive or negative. Well, 2 minus 3, that's negative. Okay, I can factor this as x plus 2x minus 1. If I plug in x equals 2, it's going to be positive here, so it's all positive. And we know a negative divided by a positive is negative. Again, if you want to compute the actual number, that's fine. I'd prefer just to know the sign. Okay? So, all I know is when x is equal to 2, I've got some negative value here. I claim that tells me what has to happen, right? If it's negative, I can't shoot up to positive infinity as I approach this vertical asymptote, because then I'd cross my x-axis again and I'd have another x-intercept. But I only have one x-intercept. So, because I found it's negative, I know that I'm going to shoot down. Now, the other portion of this graph, which is kind of funky, is we don't know as x gets large whether we're going to approach our horizontal asymptote from either some positive values or down here at negative values. So what I'm also going to do is, let's just take something bigger than that value of 3. Let's test x equals 5. Okay? Again, if I plug 5 in my numerator, it's going to be a positive. If I plug 5 here, I'm also going to have a positive number. So I know somehow what happens is I go up, but then I know I have a horizontal asymptote, so it's going to go down. Okay? And you can refine your graph, use a graphing calculator to refine it, but right now we just want to get our general ideas. All right, now let's take in here. Well, what's going to happen here? I've got my y-intercept. Well, I'm approaching a vertical asymptote. Either I'm going to shoot up or shoot down. But what do I know has to happen? I know I have to shoot up. Why? Precisely because if I went down, I'd have another x-intercept. Now, again, we know we're going to be shooting up here. We don't really know what happens in here. Like, does this go down and then go up, or do we just go up from here? Okay, but I know that it's going to approach positive infinity here precisely because I don't have an x-intercept over here. You could test -1, and that's something we could plug in actually and see. If I plug -1 in here, I get a -4. If I plug a -1 in here, well, I get 1 minus 1 minus 2. So I'm going to have -4 over -2, which is 2. In other words, it's growing. So I'm going to shoot up like that. All right, our last question. What happens over here? Well, notice we have a vertical asymptote at -2. So let's see what happens at -3. Here I'm only going to care about the sign. If I plug -3 in my numerator, it's negative. Okay, I like plugging things in my factored form usually. If I plug -3 in my first term, it's negative. Here it's negative. A negative times a negative is positive. And then I have a negative divided by a positive, which is negative. Point being, when I'm at -3, I'm down here. Well, I got my graph. How do I have my graph? Well, notice as I approach my vertical asymptote, I'm either going to shoot up or shoot down. I claim I have to shoot down because if I shot up, I'd be crossing my x-axis, and that would imply I have an x-intercept. And we have a horizontal asymptote here which says as y, as x gets really small, my function values approach. All right, let's take, how about one more example here? And then don't worry, we'll go the other way as well. What if I have y equals 2x plus 5 over 2x minus 6? Okay. Well, first off, let's find an x-intercept. How do you find the x-intercept? You set y equal to 0. Again, a fraction's only equal to 0 if your numerator is 0. We can solve for x, move your 5 over, and then divide by 2. So what do we have here? We have x is -2.5. It's the only place our graph touches or crosses our x-axis. If we want to find our y-intercept, we set x equal to 0. Well, that nixes these guys, and I claim I get -5/6. So it's about here. Okay? All right, let's talk about some asymptotes. Let's talk about our horizontal asymptote. Okay, again, in order to find your horizontal asymptote, you look at the degrees. Notice here the degree of my numerator is equal to the degree of my denominator. So it's the ratio of my leading coefficients. So it's y equals 2 over 2. In other words, it's the line y equals 1. So here's 1. And there's our horizontal asymptote. Last but not least, our vertical asymptote. That's precisely where your function is undefined. In other words, you set your denominator equal to 0. I can solve this for x, move my 6 over, divide by 2, and I have x equals 3. 1, 2, 3. Well, I claim we have half of our graph already figured out. Okay? Why? Well, notice as I approach this vertical asymptote, I'm either going to shoot up or shoot down. I can't shoot up because I don't have an x-intercept here. So I know that I'm going to go down to negative infinity. I'm going to play connect the dots, and then I know that I have a horizontal asymptote here. Why is that half of our graph? Well, precisely because since we have one vertical asymptote, half is on one side and half is on the other. How do we know what happens over here? Let's take a test point. Okay? What test point am I going to pick? I'll pick x equals 4. Now this is a pretty easy one to compute. Okay? We could just see whether it's positive or negative, but let's compute it. If I plug in 4, I have 8 plus 5 is 13. If I plug in 4 here, I have 8 minus 6 is 2. Okay? So I'm up here. Done. We got our graph. Why? Again, as I approach my vertical asymptote, I claim I've got to shoot up. Precisely because I don't have an x-intercept here. I can't shoot down. I have a horizontal asymptote there, which means as x gets large, I approach it. All right. How about this? Let's do one more just so that I know that you guys are okay with this. And then what we're going to do is go the other way around. What I'm going to do is I'll give us two graphs and we're going to find a possible formula for it. Just like what we did with our polynomials. Okay, so one more where we graph, and then we're going to do two where we're given the graph and we have to find a possible formula. All right, let's do this. Y equals x squared plus 2x minus 3 over x squared minus x minus 2. Okay, well, I know that I'm going to need to factor this. Whenever you're dealing with rational functions, you're going to want to factor. Precisely because we're going to either be setting our numerator equal to 0 in order to find our x-intercept, and we're going to be setting our denominator equal to 0 because we're going to want to find our vertical asymptote. Since I have a quadratic in both, let's factor. Okay? In factored form, I claim this is x plus 3 times x minus 1. In factored form, I claim this is x minus 2 times x plus 1. Okay? Now that we've done that, let's do our intercept. Our x-intercept. Again, to find your x-intercept, you set y equal to 0. A fraction is only equal to 0 if your numerator is equal to 0. Aren't you glad we factored this? Okay? Well, I got the product of two things equal to 0, so I claim either my first one's 0, or x is negative 3, or my second one is 0, x equals 1. So here we have two x-intercepts. Okay, y-intercept. Again, what we do is we set x equal to 0. When I want to find my y-intercept, I tend to look at it in the unfactored form, precisely because if I'm setting x equal to 0, that nixes every term that has an x in it. And I'm left with negative 3 over negative 2, which is 3/2. There we go. All right, horizontal asymptote. Consider the degrees. Notice the degree of my numerator is equal to the degree of my denominator. So my horizontal asymptote is the ratio of the leading coefficients, and 1 over 1 is 1. Okay, vertical asymptote. Set your denominator equal to 0. Fortunately, he's already factored for us. So I have 2 and negative 1. So at negative 1, I got that barrier, and at positive 2, I have that barrier. Okay, notice because I have 2 vertical asymptotes, it divides my graph into 3 separate portions. I have this side, I have the in-between, and then I have over here. This is where we take test points to get a feel for where our graph is going to be. Okay? Now, for example, I'll be playing connect the dots here. As I approach this vertical asymptote, I claim I've got to shoot up. Precisely because if I went down, that would imply that I have another x-intercept. Notice from here, I could either shoot up or shoot down. Okay, because you're allowed to cross your horizontal asymptotes when you're within. So what I would do is take a test point in between here. So I would take 3 halves. Okay, this is x equals 1, this is x equals 2. So what I'm going to do is I'm going to test x equals 3 halves. I am not going to compute it. I only care about the sign. Okay, because if it comes out positive, I know I'm shooting up. If it comes out negative, I'm shooting down. So what I would recommend you do is plug it in the factored form, because you can tell the sign, because it's going to take the sign of the larger term. If I plug 3 halves in here, that's certainly positive. Well, 3 halves minus 1, 3 halves is greater than 1, so that's positive. 3 halves minus 2, that's going to be negative. And 3 halves plus 1 is positive. A positive times a positive is positive. A negative times a positive is negative. And a positive divided by a negative is negative. I'm down here, which means I shoot down to negative infinity. Okay, got 1/3 of the graph done. Now let's head over here. Okay, again, I'm going to need to take some test points. I need to see from here, do I shoot up or do I shoot down? Well, this is -1, this is -3, so I'm going to test -2. If I plug -2 in here, it's positive. In here, it's negative. In here, it's negative. And in here, it's negative. So I claim I have a negative over a positive, which is negative. So I'm down here, which means I shoot down. And here I approach my horizontal asymptote. Okay, one more, right? We need to get this portion of our graph. Isn't it cool how all we had to do though was test 1 point and we knew this whole portion? I think it is. So this is x equals 1, this is x equals 2. We can test 3, 4, 5, whatever you want. So let us see what happens. Let's test x equals 3. Okay? If I test x equals 3, well, positive, 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 positive. We know it's positive. Okay? Now, if you want to get an idea as to whether it starts above or below your horizontal asymptote, you can certainly do that. 3 plus 3 is 6. 3 minus 1 is 2. 3 minus 2 is 1. 3 plus 1 is 4. You get 12 over 4, which is 3. So we know we're up here. I'm going to shoot up to positive infinity then and approach my horizontal asymptote. Cool. Okay, 2 more. What we're going to do now is start out with a couple graphs and we're going to find possible formulas. Okay, so here is our graph. It is going to go through the point 0, 3. And I have a horizontal asymptote at y equals 1. I'm going to also have a vertical asymptote at x equals 2, another vertical asymptote at x equals -1, and then it's going to go through this point 3. Here we'll shoot up both places, and it's also going to go through -2. Okay, we're going to work backwards. I will explain my logic as we go. Okay, notice my vertical asymptotes. Okay, that's where your function is undefined. That means that what we have is these guys as zeros in our denominator. Well, if 2 is a 0, x minus 2 is a factor. If -1 is a 0, x plus 1 is a factor. So we can get our denominator precisely from our vertical asymptotes. Now, notice we have two x-intercepts. How do you find your x-intercept? Well, the way you find your x-intercepts is you set your function equal to 0. Again, a fraction is only equal to 0 where your numerator is 0. So if 3 makes my numerator 0, x minus 3 is a factor. If -2 makes my numerator 0, that means x plus 2 is a factor. Okay, now something else. Notice we have y equals 1 as a horizontal asymptote. That means that the degree of my numerator has to be equal to the degree of my denominator, right? Because if it's greater than the degree of my numerator is greater than the degree of my denominator, there wouldn't be 1. If the degree of my numerator is less than the degree of my denominator, I would have it be y equals 0. Because it's y equals 1, I know that the ratio of my leading coefficients has to be 1. Okay, so we might have some number up here. Now, what is our one checkpoint? Our one checkpoint is that f of 0 is equal to 3. So, let's see what happens here. Let's plug in 0 and see if already it works, because then we don't really have to solve anything for k. If I plug in x equals 0, I have a -3, I have a +2, I have a -2, and I have a +1. So I have -6 over -2, which is 3. So we already have it. And here's our function. I would not multiply it out, okay? Leave it in factored form. All right, let's take another example. Okay. Now our graph is going to look like this. We are going to have a vertical asymptote at 3 and at -2. All right. Let's look at what's going on here. We only have one intercept. It's at 0, 0. That's important. Okay? Notice another thing. Y equals 0 is my horizontal asymptote. Okay? What does that tell us about the degrees? It tells us that the degree of my numerator has got to be less than the degree of my denominator. Okay? I always like to do my denominator first. Again, we use our vertical asymptotes. If 3 is a 0 of your denominator, x minus 3 is a factor. If -2 is a 0 in your denominator, that means x plus 2 is a factor. Okay, notice I have a degree 2 in my denominator. That means that my numerator has to be degree 0, in other words, some constant, or it has to be a degree 1. Why? Because the degree of my numerator we know is less than the degree of our denominator, precisely because of our horizontal asymptote. Okay? Now, what else do we have? We have that this graph goes through the point 0, 0. So, for example, how do you find your x-intercept? Well, remember, the way you find your x-intercept is you set y equal to 0. Again, a fraction is only equal to 0 if your numerator is equal to 0. So that tells me that I've got to have an x in my numerator, right? The only way this guy can be equal to 0, I can't have a constant just like 5. Why? Because then this thing would never be equal to 0. So I know that I'm going to have some number times x in my numerator. Otherwise, I wouldn't have that as an x-intercept. Okay? So, our only question is, are we okay with this? Or, you know, can we just say k is equal to 1 and let it go? Or do we actually need to find and be sure that k might not be some other different value? So, what I'm going to do is I'm just going to say, well, if this is x equals 3, I'm going to take the value of x equals 1, okay? And I'm going to plug it in. Notice, by my graph, I already know he's going to be negative. If I plug in x equals 1, I'm going to get a k up here. I'm going to get, well, 1 minus 3 is negative 2, and 1 plus 2 is 3. Okay, so I have k over negative 6. So yeah, I claim we are totally fine just letting k be equal to 1. If I let k be some negative number, then a negative divided by a negative is positive, and that would contradict our graph. All right, I know that's a lot of material. I know that this is a big topic, but I hope that this at least gave you some insights. Thank you.